Wednesday, we talked about, we compared ionic and molecular bonding. And actually, we started off talking about this sort of model for bonding, that all bonds effectively involve two atoms and a pair of electrons or a set of electrons that they have in common. But maybe this is a horrible analogy, but I look at most bonding as being like an unhappy couple that has divorced. And if you look at them, they're staying near each other, not because they're attracted to each other, right? Pluses repel pluses, but because they're attracted to the kids. And so if they're both attracted to the same set of electrons, or kids in this case, if we're talking about using my horrible divorce analogy, if there's an attraction from one atom to the shared electrons and the other atom to the same shared electrons, then they're attracted to each other. But how those electrons are shared can actually be very, very different. If we had equal electronegativities, those electrons would be right in the middle. It would be like, they would have like equal custody. They would be like alternating days of caring for them, right? And so those electrons would be right in the middle between the two nuclei, between the two atoms. However, one atom could be more electronegative than the other, and those electrons would get pulled towards them, right? And maybe this atom would only see it on alternate weekends. Who knows? But a third possibility is that this atom simply gives away the electrons completely, donates them, and simply skips town. In that case, we would have something that is more ionic. We'd have something that is wholly positive and something that is fairly negative. Now, that's just a weird analogy, but the idea is that the electronegativity difference determines what type of bonding you have. Over here, we have ionic bonding, where the electrons are donated, right? We have the metal, which gives up electrons, and we have the non-metal, which takes electrons. Here, we'd have electronegativities that are close to each other, such as two non-metals close to each other, where they share unequally. And here we have like two of the same element sharing exactly equally, right? But what I want to get to is this ionic bond. Since all we're talking about is really unequal sharing, in order to have an ionic bond, we just need really unequal electronegativities, okay? Now, if you recall, on a periodic table, electronegativity goes from the bottom left up towards the top right. So electronegativity increases until we get to fluorine, right? And so, but another thing you might want to remember from electronegativity is that all of the metalloids have an electronegativity right around 2, right? Fluorine is at 4, and these guys are all right around 2. So they're right in the middle. This guy up here is 4. I don't remember what francium is, but it's very low. And these guys are in the middle. So if I want to have a big difference, I can't just choose 2 nonmetals because they're all between 2 and 4. So instead, what I do is I simply choose a metal over here with really low electronegativity, and a nonmetal, something over here with really high electronegativity. And so an ionic bond is always going to have a metal and a nonmetal, okay? And that's the easy way of, and it's because it will have a metal, low electronegativity, and a nonmetal, high electronegativity. And that means that the electrons will simply stay with the nonmetal. The metal will simply donate those electrons, okay? So what I want you to remember, even though this is a brilliant explanation, it is brilliant. It was written by somebody who is very handsome, I'm sure. What I really want you to remember is the stuff here in the box, okay? If I want an ionic bond, I want a metal bonded to a nonmetal. If I want a covalent bond, it would be 2 nonmetals bonded. And if we look at the problems that we were working on, we had ionic compounds are composed of, what was that again? A metal and a nonmetal, right? And covalent compounds are composed of, a a nonmetal bonded to another nonmetal. Okay, so we have this written right there. And then we need to identify compounds that are either ionic or covalent. Well, you may or may not know the periodic table well enough to be able to pick things out, but calcium, it turns out, is at the left of the periodic table. Calcium is, oops, not on this chart. Calcium is over here. Here's calcium. And so calcium is definitely a metal. Right? Calcium is, in fact, a metal. And chloride, right, is over here. It is definitely a nonmetal. Okay, so when we look back at this, calcium chloride has a metal and a nonmetal, and so this is definitely ionic. Okay, so we can put an I there for ionic. Whereas CO, if we look at this guy, both C and O are nonmetals. If we look back at this, here's our C, here's our O, and so you can see that they're right near each other and they are both nonmetals. And so this guy should be covalent. What is our reason? Well, they're both nonmetals, whereas this has a metal and a nonmetal. And so as you're doing this part, please look at a periodic table and try to get comfortable with the elements that are to the left of the metalloids, the metals, and the elements to the right of the metalloids, the nonmetals. Okay. And you should be able to finish up our note packet at this point. Okay. And I think that is everything. So I will stop there.